All right, so last time we basically were able to derive the expression of the position of a point of the element with respect to the inertial frame. Now, the idea is to use this piece of information to derive the mass matrices for the elements, okay? So that eventually we will be able to reconstruct, let's say, the formulation for the multibody system that we already achieved at body level, but in this case, using the pieces of information that we resorted to develop the finite element formulation that we carried out so far. So in this respect, today we will discuss about the derivation of the mass matrix of the element. Okay. Okay, so what we were able to say is that the position ij of a point of the element j belonging to the body I has the traditional rigid translation component plus the rotation matrix AI applied this time to matrix n ij, which basically encompasses all of the formulation, acting over the vector of the nodal quantities of the elements for the overall body in its reference configuration, and then the vector of the nodal coordinates associated to the overall body I due to the deformation process, where B2I, if you remember, no, what happened? Okay, the projector has some issues. Don't know what to do. Okay. Hopefully you will be able to see anyway. Where B2I is the reference condition matrix. So basically the matrix imposing the reference condition for the element. Okay, removing all the rigid modes, which in theory could be available for the element itself. And this part, we also termed it R over bar ij, okay? So the local position of the point of the element j belonging to the body I described with respect to the body frame. Okay, if this is true, of course, it's kind of straightforward to derive the velocity of a generic point P associated to the element. So we have, as usual, a I dot. And then we have first the time derivative of the rotation matrix I, R over by ij, plus, as we know, then the derivation of this. Okay, the derivation with respect to time of R over bar basically acts only on the quantities which depend on time. So what is the only time-dependent quantity here in the square brackets? Well, basically, it's this one, okay? Because this is only due to the initial position. So it's basically dependent on time, but only with respect to the initial instant of time, okay? All of the rest, basically, is just not dependent on time. So we can basically, applying the chain rule of derivation, write the following. Okay, and this basically can in turn be written as AI, applied over. Okay, so now we know how to express, we saw it so many times, how to express the time derivative of the rotation matrix resorting to the vector of angular rotation. So basically like this, plus the second part. Okay. Okay. Now we know that you can express this vector product in terms of a matrix product. This we have done it so many times. So, oops, sorry. Okay, like this. Or otherwise, you know that we can basically invert the order of the vector product if we pre-multiply everything by -1. Okay, so we can write that this is equal to minus r over bar ij vector omega bar I, and this in turn can be written as minus r over bar tilde ij applied over the vector omega I over bar. Okay. We have seen already what these skew matrices are, but we can further clarify. So we have that this matrix here, of course, has the usual structure. Okay. So again, it's a skew matrix. So all the first principal diagonal is 0. And then we have minus R3 over bar ij. Then we have R2 over bar ij. And minus R1 over bar ij. And then it's a matrix. So it's basically like so. So nothing new. And of course, this is the vector which we consider for such construction. So R1, R2, R3 over bar ij are the components of the local vector R over bar ij. Okay? Okay, we also have the following. That we have learned to write so that the angular velocity can be written resorting to the matrix G over bar I applied over the vector theta, where this vector theta dot is basically the time derivative of the vector of the rotation parameters, for example, Euler's parameters. And therefore, if we put all of this together, we can write that omega I vector R over bar ij is minus R over bar tilde ij matrix with a minus in front times G I over bar theta I over dot. Okay. And then basically everything turns out to come in the following way. That P dot ij is just Ri dot minus A I applied over R ij tilde times G I dot I plus A I and B applied over QF. So what is my, what did I gain really formulating everything like this? Well, you see, it's the usual, it's the usual thing. I've been able to write the time derivative of the position of a point in terms of the generalized coordinates that we typically use, which are R, the translation, rigid translation vector, theta dot, rigid rotation, and then we have what? The vector of the the nodal coordinates induced by deformation, in particular with respect derived with respect to time. Okay, so we have this one here. So this is basically what we have gained. So we have this, and then we have this. And the next step is the usual one again. So basically rewrite all of this, resorting to a new vector, and have a compact formulation for all of this. So this means that we define let's say the vector of our unknowns, which are really what we were looking for, qi, which is, in a sense, just specific for the body I. That's why it only has one superscript. There's no j anymore. And this is like this. So we have this, as I was mentioning, and we have, yeah, as a matter of fact, we should put the transpose operator over everything, so to be consistent. And then we have a qfi, like so, and then everything is transposed. Okay. So this is our vector of unknowns. And so can write that our Pij is just I minus A I R over bar tilde Ij, and then we have G over bar I. And then all of this is also including this last part, An and B, 2. All of this being multiplied by what? Well, Qi dot. Okay? Yeah? And as usual, we write this in a more compact way, introducing an L, which this time, different from the L, if you remember that we have introduced when we will only describing the behavior of bodies as a whole without, encompassing the formulation of finite element methods. We have an Ij, where previously we only had I. Okay, applied over Qi dot. So you can already guess what's the next step. That's to say, evaluate the kinetic energy. Okay. So we now evaluate the kinetic energy. Of the element, of the element J. As such, so we have T Ij, which by definition is equal to 1 over 2, 1/2 of the integral over the overall body of the element Ij, density Ij, and then, as usual, Pij dot transposed apply over P dot Ij. Again, this transpose operation is just another way of rewriting a scalar product. That's it. Integrated over the volume. Okay. And this, resorting to what we have just written here, this one here, can be written in another way, more convenient, because it allows us to bring out of the integral sign all of those quantities which are not space dependent. That's to say, in the following way, Qi dot transposed, and then we have, let's say, square bracket of the integral rho Ij, then we have L matrix Ij transposed over L Ij, and then all of this integrated in the Vij. Okay. So this is basically where we're at. And as you can or should imagine now, What is it that we have here in square brackets? It's the mass matrix of the element. Okay. So this is how these things are built eventually. So M, of course, Ij. Mij is exactly what we have within square brackets. Okay. And therefore, quite straightforwardly, it becomes written as such. Sorry. Okay. So please note this thing, which is quite peculiar. You see here, we have a quantity which depends on the element. So it has a J superscript. And then we have the mass, which has the same feature. But the vectors upon which this mass matrix acts are, in fact, the same for the overall body. Okay, you see. So the J here, subscript, the dependence of specific of the element, is retained by the mass, not by the vector of the novel quantities. Okay, why is it so? It is an important thing to notice, because eventually what we're going to do after this is to assemble the mass matrix of the elements so that we're going to have the mass matrix of the body, because this is what the code does. Okay, and to do so, we can resort to the noteworthy fact that this operator acts on vectors which are the same for the overall body. So we can basically perform a group and assemble the mass matrix in a very simple way. Okay, so we can rewrite the following. My projector works now. Seems to. Yeah. So Mij, as a matter of fact, is the integral over Vij well, it's just a way to rewrite in an explicit form what we have just seen. So we have G, and then Ij, sorry. That's not Ij, of course, that's only I. Yes, of course, that's it. Okay, so this is the first, and then we have the following, which is basically the same. So we have I. Of course, the identity matrix has no dependence on I or J because it's basically always the same. And then we have something like this, G. Okay. Why did I write it in an extensive way? Because this allows us to basically identify the submatrices of the mass matrix. It's 3 times 3, so it's going to have 9 submatrices. Since it has to be symmetric for energy conservation reason, well, we're going to have only 6 independent components. Can I slide? I'll take your time. Okay, so the interesting thing that we're going to see here, why are we going to go through this again? Well, first of all, because it's not really the same thing as before, even if formally is. But what I would like to show you now, if I have enough time, is to see how the adoption of the finite element model, or the finite element method, sorry, with the correspective functions, is out the construction of the system. So did you remember that when we just used the restricted formulation, we had 23 inertia shape integrals, which are kind of a lot. Now you're going to see that if we go through this, the number of these inertia shape integrals that we have to compute every time, even if it's just once, but we have to compute every time that we perform an analysis, is reduced a lot if we use finite element method. Okay, so this is an additional advantage, which is important. So if you have to list out the advantages of the finite element method, the main three advantages. First, compatibility with boundary conditions, because they are 1 where we need, and 0 everywhere else. So we can basically fulfill and be compliant with boundary condition in a very simple way. Second, it gives the generalized coordinates physical meaning that allows us to interpret critically the values, if they actually have sense or not. Otherwise, it would be very difficult. And third, we're going to have a sensible reduction in the number of the inertia shape integrals, which are associated to this method, from 23 to much less. Okay. And this, of course, has a consequence in terms of computational time, which we save. Okay. So finite element methods are really something. And this explains somehow why they are so widespread. Okay. So in terms, some matrices. Well, it's basically what we have just seen. It only adds a subscript if you want. Do you guys remember when is the last day for the lecture? I think it's something around June 1st or something like that. Is it June the 1st? Someone nods. Yes, right? Yeah. Okay, so we're on schedule. Because eventually, basically, what was the remaining part that I wanted you to do in the few lectures which are left. So close this part and have an exercise as usual at the end of the module. So to basically implement practically these things. And then the last module is gonna regard, if we have time enough, reduced order modeling techniques. Have you ever heard about them? ROMs, ROMs, no? So reduced order modeling techniques are those techniques in which finite element models, or in general discrete models, most probably finite element models, are reduced in their size, because these models can have a number of degrees of freedom, which, even if it's not infinite, thanks to the restricted formulation, is super, super big, okay? And still, sometimes we need to save some of these computational time, more than just like this. And so what we do is to kind of condense really some parts of our models, so to reduce the numbers of degrees of freedom. And that's why these reduced order modeling techniques are also named condensation techniques. There are different, we're going to say the most popular ones, which are two, static and dynamic, also called Gaussian iron and Crane-Barton techniques. And these are things which are implemented actively in codes. they actually contribute to the formation of superelements. And this is going to be the last thing that we're going to see in the course. So basically, to close a little bit all of the part that we have gone through. OK. Let's continue. So MRR IJ. IJ. OK, and this is typically just the mass. All right. Seriously, let's say it is also important to see somehow what is the form that these operators have. For example, I'm not sure if we ever denoted this fact, but why is this constant and this is actually, when you do it, basically you have a matrix like this, M, M, and M. All right, IJ, IJ, and IJ. Or if it's for the overall bodies, it's just MI. Because basically this is the mass that participates to the motion. Okay, and when you translate body, in this case an element J, toward X, along X, Y, or Z, well, unless there are parts which are not attached, everything will follow the motion. And that's why it's the overall mass here that you can see. Okay, and this exact same physical meaning that you can see clearly here is the same that you can find in the other submatrices. Okay, so when you, for example, as we have already seen, can cancel out this term, this coupling between R and theta, when you, for example, choose, bless you, the center of mass of the body as a reference, origin of the reference frame from the local body, and you cancel this out. What does it mean? It means that you actually decouple rotation and translation, okay, in the description, all right? So it means that you either can describe translation or rotation, okay, separately. Okay, so it actually has a physical meaning, okay, what we are seeing, which is apparent in this case and maybe less apparent in the other case, but nonetheless, it's important to see it. Always on this note, is someone of you attended the class on aerospace structures with me, maybe, no? With Professor Mastrodi? Costruzioni aerospaziali? Yeah, bachelor degree. Ok, c'era anch'io? No, non ancora. Okay. Copotelli ancora, ok. So, switch to English as well. Have you ever encountered the concept of mod shapes? Of course, yes, right? Well, you also have encountered the concept of effective modal mass, I assume. No? No, never? Participation mass. Massa modale, modal mass, or massa modale effettiva. Well, okay, the effective modal mass is the mass that is actually that participates to the mode, which is involved by the mode. Okay, so for example, if you have a cantilever beam, okay, and you have the first mode of vibration, everything will basically, everything will be encompassed by the motion, because basically it's the first mode, everything moves, apart from the edge which is fixed. And so the effective modal mass in that case, we're going to be almost 100%. Okay, so when you're going to perform, for example, qualification procedure to see if a structure has a mode which has a frequency above or below a certain threshold that you have to respect, how are you going to say that if that mode that you're going to get from these finite element models is the right one for you or not? What I mean is that here you're going to have a huge number of degrees of freedom, and as a consequence, a huge number of modes. You're not going to have 2, 3, or 5. You're going to have hundreds or more. How are you going to say if one mode is actually what you need, the thing that you have to look at in order to fulfill a constraint? For example, you have to say that for a rocket, for thrust vector, you have to say that the axial vibration has to stay below 15 Hertz. Okay, how are you going to say from the, you have a table here. You don't see the shape, let's see. Okay, how are you going to say if that mode is the actual mode? How important is that in the contribution to the definition of the dynamics of the system? Well, through the effective modal mass, which is nothing less than these kind of things here. Okay, but of course translated in the perspective of the modes. And then you're going to say that when you're going to do it, for example, for Patran or Nastran, or in this case, also Adams has some flexible, some instrument to do flexible analysis. Well, you're going to have a table of modes, and then you're going to have modal mass. And the modal mass is going to be 5%. Well, if 5% is the modal mass associated to your mode shape, which has a frequency of whatever, well, probably you're not going to say that you enforce the constraint on the requirements of the frequencies if that mode satisfies the requirements. You have to say, look, I can see what is the principal motion associated to that mode, for example, axial, but then you have to look at the modal mass, which is associated to that mode. Because if, for example, if that mode only regards 5% of the mass of your spacecraft, maybe it's an appendix. It's a bracket which is doing an axial motion, okay? And if this is the case, then you're not able to say that your overall spacecraft satisfies the requirements if that mode only encompasses 5% of the effective modal mass of your structure. All right? So you have to say, you have to search, keep on searching on the list of the modes which are outputted by your code and see which one has the highest modal mass until you find an axial mode which has an effective modal mass of, say, more than 50%. Actually, the requirements which are given by ESA on this ECSS manual, which is the qualification manual, typically states a limit of 50% of mass to take into account that mode as representative of a certain behavior for which you have to fulfill a requirement. Okay. Why did I do all of this excursion? Because this is exactly the same thing. Okay. This is a participation mass for the motion that we have taken into account. In this case, it's the rigid motion. And basically, it's M, that's to say, it's the 100% of the mass. Because when you perform a rigid motion, all of the mass of the body, in this case of the element, will take part to that. Okay, since it's a rigid motion. Okay, it's the same concept, and as in the case of mode shapes, it's key to understand if your formulation is correct or not. Okay, and if it makes sense or not. Okay, let's keep going. All right. AI and IJ B to I. Okay. And then we have, okay, we write them here, M theta theta. Okay, so this is M, theta theta, and then we have the last two. I saw that some of you nodded when I cited the ECSS manual. So you do know the spacecraft design. Ok, and that's it. This is the only. Questo è l'unico corso sul quale siete esposti su questa roba. Siete costretti. Ah, perché è obbligatorio?
No, a seguire il manuale, non il corso.
Ah! okay? Perché praticamente per chi andrà a fare lo strutturista, questa è la verifica dei requirements sugli standard internazionali, è il lavoro che farete al 70%. Ok. Transpose, then we have R. Okay. Is transposed, then we have B2, and that's it. Okay, so these are all the sum matrices, and we're going to briefly go through them, because again, what I want to show you now is just not to complete this part per se, but really want to show you that we have a practical advantage another practical advantage in using finite element methods also with this respect. Okay, so here we have this, as we know, we have just written it, and so, as I was mentioning before, this amounts to mi, which is the total mass of the body, times the identity matrix. Okay, so this is the total mass of the body. So all of the mass, so here the effective modal mass is 100%. Of course, sorry, this is, we miss a J as well, of course. So the total mass of the element J. Okay. Okay, this is, okay. I think it's super simple to understand, as we have already done. Okay, then rotation matrix. Not really the rotation matrix, the matrix associated to the coupling between rotation and translation, rigid. As you typically do, we take out from the integral sign all of the quantities which do not depend on space, namely all of those which only depends on rotation in this case. And so we write like this: by square brackets of the integral over the volume, the density, and then V J. Right, then we have G. And this we typically write as minus A, I, then we have a vector I over tilde ij, and a G. Again, this is something that can be resorted to a unit vector, a vector quantity. So this is a matrix which leaves Dij. Okay, by definition. Is by definition. And therefore, we can associate to this, because we have R over bar tilde, we can associate to this the vector counterpart, which is I. So we associate to this quantity this, in the same way we associate to this quantity, this matrix R over bar. That's just the same thing. And this, of course, stands defined like so. Oh, sorry, it's a vector. I just said it. Okay. Why do we do this? Because, of course, this is much easier to treat. And what I wanted to, let's say, express here is that basically the quantities which we have in these matrices are scattered in a skew way of the components of this. So if we know how to calculate this, we can construct this very easily. Okay. So what is this vector again? This vector is the following. It's the integral of Vij on the density Ij. Let's bring out the element structure. Applied over QFI, the Vi. And this can be written as S, the matrix S over bar Ij psi, applied over Qi, 0, plus S psi over bar Ij, again, applied over B2I, QFI. Okay. Where S psi I, by definition, is the integral over Vij or rho Ij n Ij dVij. In fact, we can unpack n. We can also write it like this. C2, you remember, it's a constant matrix. And then we get the integral over Vij of the density. And then the psi, you see, here we go back to the roots where basically we have the element shape functions. And then we have C1 Ij, B1 Ij. And this is the first inertia shape integral of the element. Okay, so you can already notice, you should already notice one thing, that when we went through the same exact topic, but at body level, we had already here two inertia shape integrals. One was here and one was here. There were two. Now it's already just one. Okay, so we are already saving some computation. Let's go briefly through the rest. Mm-hmm.
Is there a J-lac?
There is, of course. Yes. There is. Thank you. Three. M art F. Well, by definition, again, we take into account the density, rotation, N, then we have B, and then we have the Bij. Again, we bring out the integral sign quantities which are not directly space dependent. Okay. And again, you can see that we have, again, the same shape function of before. It's the same again. Hmm? 4 theta theta. We bring out again non-space dependent quantities. That's to say the G, in fact. And we cap the rest. So the density Ij. And typically we use the following notation. What is this vector here? I theta theta Ij. That's the inertia tensor for the element. Okay. We'll cut it short here. And if you further develop this quantity, you can see that this constant inertia tensor of the element J can be written in terms of 6 inertia shape functions. So we can say this. This can be demonstrated. In fact, I think some hint to this there is in the notes. But it is not important that you are able, that you go through all this algebra. Important is that you understand the concept. The following 6 inertia shape integrals are required to derive the inertia tensor of the element J, which are the following. S, always a matrix, Ij again, Psi, Psi, KL. So again, Psi and Psi are just a subscript which is fixed. It's not an index. It's just a notation. It doesn't roll. Why am I saying 6? If K and L typically roll from 1 to 3, you should have 9. Well, of course, there's going to be some symmetry reasoning in the middle, as you can imagine. And in fact, if this is the case, we have this. Oops, sorry, that's like this. K transpose ij applied over n L ij in dv ij. Okay, and this of course can be written also as b1 ij transposed applied over c1 ij transposed, all of this being applied over the integral over the volume of our body of what? Of c k, sorry, c k transposed ij applied over psi L ij integrated over the volume of our element C1 ij B1 ij. So what are these K and L? These are row vectors. These are not column vectors. This is the kth or the lth row of the matrix N or of the element chain matrix Psi. As a matter of fact, when you perform this matrix operation, in fact, you don't have a scalar quantity because these are not column vectors, these are row vectors. Well, when you do this matrix multiplication, you get a matrix. So let's write it down. So, well, nkij is the kth row of n ij, and C as well is the kth row of the matrix ij. Okay. So why 6? Well, if I exchange k with L, doesn't change anything, all right? So if I invert the order of the subscript, I have the same quantity, meaning that I have symmetry. So no 9, but 6 independent parameters. Okay. All right. Let's keep going. So far we are up to 7 inertial shape integrals instead of 23. Let's see if we need any more to close the formulation. Ij, B2. Okay. So again, I'm just bringing out non-space dependent quantities from the integral sign. So where basically we can now define the following. This quantity here applied over nij, which we have here, can be written as such. QE I transpose. Remember that here we have, of course, if you go and check, you have the vector of another quantities, right? I mean, for those of you who do not remember this, we have this. We have that R over bar ij, so the vector, we expressed it like so. To go and check to previous lecture, we have this. Then we introduce also B2 when we basically referred to the reference matrix as well. We introduced the reference matrix. But N, in fact, was introduced at this point. And that's why here we find this vector QE. Okay. All right. So we have N2 ij transposed applied over N3 ij minus N3 ij transposed applied over N2 ij. And this is the first one. We get basically the following. Qi transposed applied. Always the vector. We have 3 and 1. Okay, and then last, still QE IT, and we have what? We're going to have 1 and 2. 1, 2, 2, 1. IJ, IJ, J, IJ. Okay, why am I doing this? Because now with this expression we can introduce a quantity. Which is the following. Can I slide? We're almost there. Hang on. And KL over bar ij just basically as the quantity which we have encountered so far. K ij transposed L minus K so what we have basically in the matrix before, and therefore M theta f I j can be written as G in a more compact way, and QE I transposed applied over N23 over bar tilde, QE I transposed applied over N31 ij, and QE I N12 ij applied over B2. This, if you go and check, is exactly as psi k l I j. Okay, so we don't need, we still are up to 7. Okay, so we only are left with 1, and then we're done. I would say one of the easiest.
Ma dovrebbe esserci un trasposto tra G.
No, there should. Yes, 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 correct. Yes, because it's here. It's here. It's here, it's here, and so yes. Yes, yes, yes. Thank you. Okay. Last, this is very simple. 6. MFFI. Of rho ij. Just for the sake of clarity, I'm not going to ask you at the exam to remember all of this by heart, of course, right? So what I can ask you is giving you a starting point if you're able to elaborate further with some calculation, okay? I don't demand you to have this in mind, of course. It would be crazy and useless, okay? But I can, of course, and I will ask you questions on the logic part of this, okay? So for example, why FEM method delivers an advantage in terms of inertial shape integrals with respect to the classic restricted formulation. And now we're going to see it. These things, of course, yes. But as for the all the algebraic passage, it's just for me to show you that logically we can arrive there somehow, okay? But then you don't need to answer to remember for that, you know, by heart, even because 1 week after the exam, everything will be lost probably. All right. I want you to have the concepts. All right, still. So again, we bring out everything which is not space dependent, and we can write the integral of the Vij of rho ij and ij transposed and ij in Vij in B2. And this can be written as such: B2 I transposed applied over what? S psi psi over bar ij 1 1 plus S over bar ij psi psi 2 2 plus S ij psi psi 3 3 multiplied by B2 I. Okay, let's see. And of course, everything here is constant in time. Why do we have this? Why do we only have you know, quantities which have the same indexes? We have already hinted at that when we saw this at body level. You have to remember this. If you don't immediately see it, we had that, if you remember, our vector of the displacement induced by deformation could be written as then we have ck r0 over bar, and then we have qk of time, and therefore we had the psi scalar, or if you want, transposed and then applied over psi j is either 0 if E is different from j, or, well, different from 0. 1, if it's orthonormal, you can normalize whatever these quantities. If phi is the same of j, okay? So these shape functions, which in our case are the finite element method shape functions, which are inside our n, as we have seen, still retain this property y, because they are a basis. Being a basis, they are independent. Okay, so what is the concept of independence for a function? That the integral of the two is either 0 or not. It must be 0 if they are independent. Okay, that's why here we only have quantities which are referred, you see here, with the same indices. Okay, in any case, apart from this, which is a similar result to what we had in fact achieved, we have found out that how many inertial shape integrals are there needed eventually? 7, only 7, instead of 23. That's 1/3. Huh? Less than 1/3. So that's a big advantage. Now, someone of you may say, well, right, we only need 7 of these quantities instead of 23, but those 23 were for the overall body. Now these are only for one element. So we have to compute 7 for each element, which is quite a number then eventually. True. But those quantities, those for the bodies, had to be calculated performing an integration over the entire domain of the body. Here, the integral has to be performed only on the single domain of the element. So it's much, much faster. It's easier. Okay. So that eventually the integration, computational time, which is needed for one inertial shape integral for the overall body and the sum of the overall inertial shape integral for the element that form one body is the same. So 1 to 1, we have this, let's say, relationship in terms of computational time. But again, in the general restricted formulation, we have 23, here only 7. So in total, at the end, we still gain time, and a lot of time. Okay. 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 And these are one vector, which we define as such. Very simple. And then matrix quantities. Of course, with K here and L that always go from 1 to 2 and to 3. Okay, so with this, basically we are able now to define the mass matrix for the element. So we calculate these 7 quantities once, and then we're done, basically. We can re-update the mass matrix of the element at each time, following these analytical, basically, expressions without reperforming integration for each element. Okay, so what is the next step? The next step, as I suggested at the very first start of the lecture, is to assemble all of these mass matrices. And we can do it in a very, very simple way, thanks to the way we have formulated this part. Let's see how. Let's start to see how. So this part we can only start today. Yeah, we don't have much time left. But the topic is the assembly of the elements mass matrices. So we have that the kinetic energy of the overall body I is just the sum from J going from 1 to the number of the elements, NE, or whatever you want to call them, of Tij, which we have defined before. So the kinetic energy possessed by the whole of the body is the sum of the kinetic energy of the elements. That's it. All of them. So this is number of elements of the body. This is the kinetic energy of the body. Well, this can be written kind of easily. Right? Now, why did I stress out the fact that here, when we express the kinetic energy of the element, well, in fact, we operate over quantities which are defined for the overall body, retaining the information of the element only to the mass matrix. Because now we can put and group the sum sign only to M and put this and this outside of the sum, right? So we can say 1 over Q dot I transposed applied over the sum from J going from 1 to NE of M Ij applied over Q I dot. Huh? And then we define Mi as the sum from J going from 1 to NE of Mij. The assembly of the mass matrix of the body is as simple as that. It's just a sum. It's not bad. Okay, I think we can end the lecture here for today, a little bit early. We save 5 minutes.